Let's talk about motor generator characteristic curve or motor power torque curve, also known as idle peak torque curve. So to begin with, I'll just show you a small explanation over paint and then we'll jump on to Excel for some calculations. So in this image, you can see ideal peak torque curve of a motor. For generator, it's a mirror image over the horizontal axis. So there are a few terms which we need to be careful about. So first one is TE or TP. This is known as peak torque. Then this is power. This line represents peak power. In this graph, x-axis is RPM, y-axis is torque or power. In the first region, till this point, till W base, this is known as base speed. So till WB, we can see that we are in a constant torque region. Beyond this point, we are in a constant power region. So, and at this point, if you notice, the value of power torque and base speed can be related. So peak power, I'll call it PP, is equals to peak torque times W base. Now in this entire region, power is constant as speed is increasing. With this relation, you can clearly see torque should decrease in order to make power constant. And that is what is happening here. So as power is constant here, speed is increasing, torque needs to decrease to maintain the same power. In the initial region, you can see torque is constant, speed is increasing. Again, by the same formula, power equals to torque times RPM. You have this kind of power characteristic. So power keeps on increasing as speed increases because torque is constant. Now, in order to represent this curve, this idle motor torque curve, we just need few parameters to be known. So let's see what are the parameters we can identify in this section. One is this max RPM, then we have base speed, then we have peak torque, and then we have peak power. So there are four variables. This is peak torque. Then second variable is peak power. Third variable is base speed. And fourth is omega max, max speed or max RPM. So there are four quantities which can characterize this curve, but out of these you can see there is this relation: peak power is equals to peak torque times base speed. So we only need two out of these three variables and one of these. So if we can get this 2 plus 1, three variables, we can create this entire curve. And that is what we're gonna see in the Excel explanation coming up next. So let's do a quick exercise. We'll assume some values of those quantities and then we'll create a curve. So let's begin. Uh, let's consider a motor with a peak power of 10 kilowatts, uh, base base speed of 4000 rpm, and max speed of 10,000 rpm. We know these three quantities, and we need to create that curve which we saw in the previous few moments. So we'll use that relation, power equals to torque times base speed, to get peak torque here. So peak torque is equals to peak power times 1000, as we are working with power in kilowatt. So this makes power in watts, divided by 4000, and then there's a unit conversion factor which is 60 by 2 pi. So 60 by 2 pi. So this gives us a peak torque of 23.86 Newton meter. Can just do a quick check. So peak torque times base speed times 2 into 22 plus 7 to 1 by 60,000. This gives us 10 kilowatt which we wanted. Okay, so this verifies the calculation. Now we need to create a RPM versus torque versus power curve. Let's enter RPM at an interval of 500. Max RPM is 10,000. Peak torque is 23.86. So I'll point to this value. It remains 23.86 till this base speed, which is 4000. So torque remains the same till 4000 rpm, and beyond that power is constant, so that means the product of rpm and torque is constant. So then we can simply calculate torque at this rpm by multiplying these two and then dividing it by this rpm. So 4000 times 3.86364 divided by rpm, and then we can copy the same formula till the end. At 10,000 we need to restrict the rpm, so we'll make it 0, or we can add another point which is offset by 100 rpm, and we can enter a value of 0 there. So this will make sure that we have some limitations on what is the max torque, uh, max rpm it can operate at. Power is torque times rpm times conversion factor 2 pi by 60,000. So we get this curve. Now let's quickly plot these quantities and see if we can get similar curve. Okay. One more thing we can do is maybe change the axes, and that's how we get this curve. Uh, One more thing that we wanted to address was the generator characteristic curve. So that is, as I mentioned, a mirror image of this curve along the x-axis or the horizontal axis here. So we just need to multiply this torque n power with a negative 1 value, so we get the mirror image. Let's do that. And now if we plot this, we'll get ideal generator characteristic curve. There you go. Again, we'll remove the last point for power, move it to secondary axis, and this is generator characteristic curve or ideal torque speed curve for generator. I hope this video was helpful. Thanks for watching. See you in the next video. Bye bye.